In this video, I will show you how to find the extrema on a closed interval using derivatives. So first of all, what are extrema? Extrema are the minimums and maximums of a function. So let's go ahead and take a look at the actual definition. F at c is the minimum of f on the interval if f at c is less than or equal to f of x for all x in the interval. F at c is the maximum of f on the interval if f at c is greater than or equal to f of x for all x in the interval. So that's a lot of words for a very simple concept. Take a look. For this function, the minimum value is right here at the point 3, 2. Now, according to the definition, the minimum is just the y value, f at c. So the y value here is the 2. So we would say that the minimum is 2. However, the very textbook where I found this definition tends to give the answers as a full ordered pair. So you might see the answer written like this. So if you're in a class and you have a teacher, you need to ask your teacher whether or not your extrema should be given as just a y value or the full ordered pair. If you're taking a multiple choice test or something like that, if it's a single number, it's going to just be the y value. But if it's an ordered pair, then obviously it's the x and the y value. All right, now look at this example. So this problem has a maximum value right here. So we would say we have a maximum value at the point 3, 4, and really, technically, the maximum is 4. Okay, but you might also see it written as 3, 4. In calculus, most of the time, we are dealing with a specific interval, part of the whole function. And some intervals are closed intervals and others are open intervals. This function is defined on the closed interval from -1 to 2. Closed interval just means that the endpoints are included in the function. And we show that by using square brackets like these. And sometimes they even put square brackets right on the x-axis, indicating the function goes from here to here, including the endpoints. So when you have a closed interval, the extrema may not simply be at the bottom of a valley or at the top of a hill. Now the endpoints themselves may be the maximum or the minimum, so you have to take that into account. So for this problem, the maximum is going to be right here. All right, the maximum is the endpoint because this is the highest point of the function. So we would say this is the maximum. And I'm just going to go ahead and say 2, 5. And the minimum is right here. At the point 0, 1. This function is defined on the open interval -1 to 2. The open interval means that the endpoints are not included in the function, and we show that graphically by having the endpoints be open circles. When we write it down, we show an open interval by using rounded parentheses like these. Sometimes you'll even see those parentheses right on the x-axis. So be careful. This endpoint way up high is not the maximum. This is not a maximum value. It can't be because this point is not part of the function at all. That's why it's an open circle. In fact, this function has no maximum. The function does have a minimum right here at the point 0, 1. For this problem, we are back to the closed interval from -1 to 2. However, does this problem have a minimum value? No, there is no minimum because the point at the very bottom is not included in the function. See the open circle? So there is no minimum. Of course, there's still a maximum value, which is still the endpoint up here at 2, 5. In a moment, I'll be teaching you how to find the extrema using derivatives, but first we need to talk about what a critical number is. Let function f be defined at c. If f prime at c is equal to 0, or if f prime at c is undefined, then c is a critical number. So of course, f prime, we're talking about the derivative of the function at c. So here are the two situations that I'm talking about. So imagine that we have a function that forms a smooth curve like this. Let's talk about the situation where f prime is equal to 0. The derivative is the slope of the function. So the slope of the function will be 0 right here. Okay, at the tangent line, when you have a horizontal tangent line. So that means this point right here where the slope is 0 is going to be a critical value. The x value here will be a critical value. Now, here's the other situation. The situation where the derivative is undefined. That will often happen, for example, when the function makes a sharp turn like this. At this point right here, you can't take the derivative at point C. That makes this a critical value as well. So one more time, critical numbers are numbers where the derivative is equal to 0 or undefined. Note, extrema only occur at critical numbers and endpoints. So example 1, find the extrema of f of x equals 3x to the 4th power minus 4x to the 3rd power on the interval -1 to 2, the closed interval from -1 to 2. Since the extrema only occur at critical numbers, that means the extrema will only occur where the derivative is either equal to 0 or undefined. So it's all about the derivative, so that's going to be our first step. So let's find f prime of x. Of course, we're just going to use the power rule. So 4 times 3 is 12. And then we'll reduce by 1. So that'll be 12x to the 3rd power. And then 3 times 4 is 12. And reduce by 1. So this is the derivative. We can already tell that there will be no values where the derivative is undefined. So we can sort of forget about this option right here. So all we have to worry about is where will the derivative be equal to 0. So let's go ahead and just set this equal to 0. All right, so if we go 12x to the 3rd power minus 12x squared equals 0, we can solve this and find critical values. let's take out the GCF of 12x and 12x squared. Put that out front. That's going to leave on the inside simply x minus 1. Now, by the zero product property, that tells us that we can get a solution by setting the 12x squared equal to 0, and we can get a solution by setting x minus 1 equal to 0. So of course this will mean that x squared is equal to 0, which means that x equals 0. So this is a critical value. Of course, adding 1 to both sides gives us x equals 1. So here we have two critical values. Since the extrema can only occur at critical numbers or endpoints, all we have to do is evaluate the original function at these four numbers, and that will give us the extrema, because the highest value will be the maximum and the lowest value will be the minimum. Make sure you are using the original function for this, not the derivative. So the left endpoint, if we substitute -1 for x, that's going to wind up giving us 7. Similarly, if we evaluate f of x at the two critical numbers and the right endpoint, we get 0, -1, and 16. So that means -1 is the minimum and 16 is the maximum. These are the extrema. Let's see if we can use this information to make a rough sketch. So -1, 7 would be about here. 0, 0 is here. 1, -1 would just be about here. And 2, 16 would be up here. So the graph would look something like this. All right, let's check this electronically. So here's a better look at the graph, and you can see our maximum right here at 2, 16. And you can see our minimum right here, as predicted, at the point 1, -1. Let's do two more examples. Find the extrema of f of x equals 2x minus 3x to the 2/3 power on the closed interval from -1 to 3. Now, remember, it is all about the derivative, because the critical numbers happen when the derivative is either equal to 0 or undefined. So first we have to find the derivative. For the first term, the derivative is just 2. For the second term, we need to do the power rule. So I'm going to take this 2/3 and multiply it by 3. 2/3 times 3 is just going to be 2. So I'm going to wind up with minus 2x to the, and I need to reduce this by 1. Hopefully everyone understands that if I take 2/3 and I subtract 1, I'm going to end up with -1/3. If you need one little extra boost, it's because 1 is the same as 3/3. So that's why I'm getting -1/3. To really see what's going on, let's rewrite this so that we don't have a negative exponent. This will be the same thing as 2 minus 2 over x to the 1/3 power. Of course, a negative power drops you right down to the denominator. At a glance, we can see our first critical number because critical numbers will occur where the derivative is undefined. And this expression will be undefined if x is equal to 0. You can't divide by 0. So our first critical number is x equals 0. We will get more critical numbers by setting the derivative equal to 0 and solving. So let's go ahead and do that now. If we do 2 minus 2 over x to the 1/3 power is equal to 0, all right, that is a sloppy 0, but you understand. Next, I really want to add this part. All right, I'm going to take my negative 2 over x to the 1/3 power, and I'm going to add this to both sides. So I'm going to end up with 2 equals 2 over x to the 1/3 power. All right, now there's something that I've learned, which is, I guess, kind of a shortcut, but it comes up so often that I want you to be comfortable with it. If I have A is equal to B over C, you can always swap these two, and it will still be a valid equation. So I can have C is equal to B over A. If you play around with it, you'll find that this always works. But as a shortcut, if we use that principle, I'm going to end up swapping these two quantities. So I'm going to have x to the 1/3 power over here by itself, and then I'm going to wind up with 2 over 2 because this 2 will end up in the denominator. So that means we have x to the 1/3 power is equal to 1. So you can probably tell by common sense that this is going to end up being x is equal to 1. Technically, we are raising both sides to the 3rd power. So if I raise the left side to the 3rd power and I cube the right side, these cancel each other out, right? So I end up with x is equal to 1. And this is our second critical value. It's time to make our table of values. Of course, we have the 2 critical numbers that we just found, but don't forget about the endpoints from the original interval, the -1 and the 3. So that's where this -1 and 3 are coming from. Also, don't forget that we are evaluating the original function at these critical numbers. So if we evaluate at -1, that's going to be like this. 2 times -1 minus 3 times -1 to the 2/3 power. If you grind that out, it's going to come out to be -5. Similarly, at the other critical values and the right endpoint, we get 0, -1, and -0.24. Obviously, I cheated and used a calculator on this last one to get the decimal approximation. So these are the extrema. The minimum is here at -1, -5, and the maximum is at 0, 0. Let's take a look at this graphically. Here's what the graph looked like. Notice your 4 critical numbers. Of course, you've got the endpoints, but these 2 blue points are the critical numbers where the derivative was either 0 or undefined. And specifically, you can see that this is the critical value where the derivative was 0. You can see right here the slope of the tangent is 0. And this is the critical value where the derivative was undefined, because the derivative is always going to be undefined at a sharp turn like this. Anyway, let's focus on those extrema. The minimum is one of the endpoints, -1, -5. So we can see that this is the minimum. And we can see that the maximum is this sharp corner right here at 0, 0. I was going to do one more problem, but this video is long enough. So you can see this problem on the next video.